Sorry, are there any questions? Okay,
What chapter are we specifically supposed to be on right now?
8.
So we have buoyancy for lab on Thursday. That's 13.
Right. You want me to rush ahead, get to chapter 13 by the end of today?
No.
That was a vote for no?
That was my point exactly. Am I supposed to have already been to 13 already?
No, I mean, the lab and the classes get out of sync sometimes.
Alright. I'm just checking, cause I didn't wanna. That's it.
I mean,
Did you get my email? Cause I thought I had it all down pat, cause I'm not driving today.
Oh.
I thought I picked up everything and I did not have,
yeah, I did see that.
okay.
Yeah. Well, why don't we just talk a little bit about buoyancy?
We don't have to.
What do you want, Latoya?
Well, I did not, well, first of all, okay, this is around that time, okay, so you know I'm real sensitive. And I was just asking a question.
Okay.
I just wanted to know, why are we on buoyancy if you're about to be talking about freaking rotational inertia and things like that?
It's the way things sync up sometimes.
So I would go on, that was it.
Okay.
But if you would like to entertain us, so when we get to Thursday, we won't be walking around with like some deers in the headlight. Anybody on 13? Then that'll be all right.
Okay. I can talk about buoyancy. Just a little bit of a sneak preview of what's coming up.
Sneaky, all right. 'Cause this snuck up on me today.
So,
I hope you feel better.
Thanks.
that's an object in a glass of water. It can be any fluid here. This is any fluid. Water is the one that you most likely be working with. But buoyancy also works in any fluid as just mentioned, and a fluid is a gas or a liquid. So we talked about if you stand on a scale, the scale actually measures the normal force you exert on it. And we generally claim that if you're standing in equilibrium, that the scale would be measuring your weight. That normal force and weight are the same thing. They're equal to each other. So person on scale, if you did a force diagram, you have weight acting down, you have normal force acting up, and scale, and then that normal force acting down. So the scale is reading this force right here. Now, that was all well and good, but as we'll get to at some point today, if things are traveling in a circle, you're not in equilibrium. And we are traveling in a circle. At least, assuming the Earth is spinning, which I'm assuming. So, these two are actually just a little bit off, out of whack. So if I'm standing on a scale, my weight is actually slightly more than what the scale is reading. So that's the first bit of reality that as we start getting into more and more complicated systems, it's just a little touch of reality. The other touch of reality is the fact that there is a net force acting upwards on anything in a fluid. And since air is a fluid, air is pushing up on us a little bit. So there's this buoyant force acting up. Generally, when we get there, we've talked about F-town. We in essence have Facebook down. Or best friend down if you want to flip the letters around. We are introducing a new force that you would at that point, you'd introduce a new force to throw into the force diagrams. Now, the buoyant force depends upon what it's soaking in. So the buoyant force of a block in water is different than the buoyant force of a block in mercury. Mercury is denser. If you look at the forces involved here, if you think about this water right here and the water right here, or the fluid, whatever it happens to be, and let's really stunningly visualize this. Ooh, colors. This water right here has some weight to it. If you've ever gone to the bottom of a deep end, at some point in my life, it started definitely feeling it in my ears. It started to hurt the deeper I went. That's because the water on top of you has weight to it. Just like the air on top of us has weight. We just, we have evolved that we're used to it. So the deeper you go, there's more and more pressure the farther down you go. And because there's more pressure the farther down you go, that means that, well, let's talk a little bit about pressure. Pressure is force divided by area. So if the pressure is greater the deeper you go, that means that the force it exerts on the surface, on the bottom of this, is greater than the force on the top. Because the pressure down here, we'll just call it PL for lower and PU for upper, the lower pressure ultimately means there's a bigger force beneath it than upper pressure. And therefore, since the pressures are different, because, and therefore the forces acting on the top and bottom are different, there's a net force between the two, and it's an upward force. Now, the amount of the buoyant force is just the weight of the displaced fluid. So then the question is, if I stick a block in a cup of water here, what's the weight of that water that I just shoved out of the way? How much water would have been here had this not been here? Well, I know weight is equal to mg, so this is mass of the displaced fluid, water in my example there. And mass relates to another thing called density. So density, this is the letter rho, R-H-O. It's the symbol for density. Some textbooks use just the letter D, but rho is what I see more often. That's mass divided by the volume. And so, if density is mass divided by volume, then the mass is just the density times the volume. So if I know what my density is, it's my density is roughly that of water, times my volume, I can find my mass. Or I can find my volume if I know my density and the mass. If I know two of these things, I can find the third thing. So this is just the density of the fluid times the volume of the object, because that's how much water got shoved out of the way, times the acceleration due to gravity. So we have a formula here for buoyant force. So I claim my weight somewhere around 980 newtons. Ish. That relates to a mass of about 100 kilograms. My density is roughly 1,000 kilograms per cubic meter. And I know that because my density is about that of water. And so my volume, so I have 1,000 is equal to 100 over my volume. A little bit of spoiler for something I generally do later, but. What is my volume?
Would it be 1,000 times 100?
Nope, wrong math operation. 100 divided by what gets you 1,000?
Is it 0.1?
It is 0.1. 0.1 what? What are the units?
Liters?
You said liters? No, that would be,
Is it kilogram?
no, that would be unit of mass. Liter is a unit of volume,
Oh,
but I think you're off by a factor of 1,000.
Milliliter?
Now you're off by a factor of 1,000,000.
Oh.
Now, let's think about this. We're talking about me. A milliliter is 1 cubic centimeter. I do not have a volume of 0.1 cubic centimeters.
so it gotta be like, like, I was about to say like decameters or something like that, but no. Sorry. Never mind.
All right, so here's one rule of thumb. Generally, if it's a one-dimensional thing, if I'm looking at a length here, my unit is gonna be something like meters. I just have one of them. If I'm looking at an area where I multiply a length times a length, I now have meters squared. If I'm doing volume, where I've got a length, width, and height, I'm now multiplying 3 meters together. So cubic meters.
So it still was meters, but we just had to cube it.
Exactly, because we're dealing with a three-dimensional issue there. So if I take, that's 1 meter by 1 meter. By 1 meter. So these are sort of map out the edges of 1 cubic meter. So from there to here, down, over. I'm hoping that you can visualize what roughly 1 cubic meter looks like. This is saying that if I were pureed and stuck into this box, I would fill it up to here. That's my volume. All right, so to figure out what the buoyant force acting on me is, my density, this is the density of the fluid, density of air, and what are the chances? Is on the front or back cover here. Slim to none. It's gonna go off of memory, but I'm not really fond of that idea either. See, gases is chapter 14, I think. Yes. There's a table of common densities. Let's see. Air. Air has a density of, in this room right now, about 1.21 kilograms per cubic meter. So density of air, 1.21 kilograms per cubic meter. I'm plugging it into this formula right here. So the buoyant force acting on me is the density of air, 1.21 kilograms per meter cubed, times the volume of air that I'm taking up, about 0.1 cubic meters, times acceleration due to gravity, 9.8 meters per second squared. And you multiply that out. It's 1 point something.
$1.1858.
And units?
KGMQ?
Nope.
Sorry, no.
Yeah, that cubic meter there cancels out with that cubic meter.
Okay, so just kilograms?
That unit's over here too.
Is it a Newton?
It would be newtons. Or kilogram meters per second squared,
Okay.
but it's a force, so newtons. So my weight is about 980 newtons. But in reality, it's off that, if I stand on a scale, the scale would be off by a little more than 1 Newton. So this is how much the buoyant force is actually holding me up. So that's sort of a brief introduction to it. So I think I suspect in that lab, you're gonna find the mass of an object by putting it on a balance, and then you're gonna put it in water, and there's gonna be a difference in the mass, because there's now a buoyant force acting up on it. And then from that difference in what the mass measures, that actually is gonna relate to the volume of the object itself. If you're doing the lab, I think you're gonna do.
That's a lot of pages in last week.
So it's enough like the one I had written for it to look familiar, but there are enough variations.
So both of them that he posted are two different ones?
PDF and another one.
Okay.
That's fine.
Okay.
The changes in the lab, was that a reference to my comments about it's different?
You uploaded 2 on Blackboard, and one's a PDF and one's Word, so you can, but they're the same one.
Oh, okay. Any questions?
What unit are we starting today? 8?
We're gonna continue in 7, we'll get to 8 at some point. And that we'll use as a segue into chapter 8, or what we're gonna do with chapter 8.
When is our next quiz?
When we're done with 10. The next quiz will be a 3-chapter quiz, 8, 9, and 10. And that comes from, traditionally, when I was doing this, 8, 9, and 10, I kept flipping back and forth between the chapters as opposed to doing 8, then 9, then 10. I've sort of been ironed out, so I'm pretty much doing 8, then 9, then 10, but occasionally they just get mixed up.